Welcome to an introduction to differential equations. The goals of this video are to determine a general and a particular solution to a differential equation in the form of dy dx equals f of x. A differential equation is an equation that contains derivatives, and here are three examples. To solve a differential equation, we want to determine an equation that satisfies the derivative equation, and this will require integration. So to solve a differential equation in this form, it's helpful to write it in Leibniz notation and then in differential form. Remember, if dy dx equals f of x, then dy is equal to f of x dx. Once it's in this form, we can integrate both sides of the equation, which will allow us to solve the differential equation. Let's go and take a look at how this is done. So the goal here is to find a function that satisfies this differential equation. Even though you may be able to solve this just by looking, let's go ahead and show the steps. The first thing we do is we write this in Leibniz notation, so we'd have dy dx equals 2x, and then in differential form we would have dy equals 2x dx. Now we'll integrate both sides of the equation, and it may help to put a 1 here so you can think that we want the antiderivative of 1 with respect to y. Well, that would just be y, and then on the right side, the antiderivative of 2x with respect to x would be 2 times x squared over 2, and then plus c. Now I could have had a plus c on the left and the right, and then combine them on the right side, but it still would just be a constant. So let's go ahead and clean this up. We have the function y is equal to x squared plus c. Notice our solution is a family of functions, and this is called a general solution to a differential equation. Sometimes we're given enough information to determine the constant of integration, as we see here that y1 is equal to 3. So we can use this information to find the value of c. When x is equal to 1, y is equal to 3. So we would have 3 equals 1 squared plus c. So we'd have c equals 2, which means y equals x squared plus 2. And this is called the particular solution. Let's go and take a look at the graph of what we just found. One way to represent a differential equation is by a slope field, as we see here in red. Each segment here represents the slope of the solution to the differential equation. Remember, we said on the previous screen that the general solution is y equals x squared plus c. Well, this represents a family of functions for different values of c, meaning any of the parabolas that fit nicely in this slope field as we see here would be part of the general solution. But since we were given that the solution passed through the point 1, 3, as we see here, this parabola represents the particular solution, y equals x squared plus 2. Let's go and take a look at another example. So here we would have dy dx equals 1 over x, which means that differential y is equal to 1 over x times differential x. So now we can integrate both sides of the equation. The antiderivative of 1 with respect to y would be y. The antiderivative of 1 over x would be natural log x, and then of course we have the plus c. Again, this is our general solution to this differential equation, but now we are given information to determine the particular solution. F of e is equal to 2. So when x is e, y is equal to 2. And that'll allow us to find the value of c. So we'll have 2 equals natural log e plus c. Well, natural log e is equal to 1, so we have c equals 1, which tells us that our particular solution would be y equals natural log x plus 1. And again, let's take a look at the graph of that. Here we have the slope field for the differential equation, and in black we have the particular solution because we were given that the solution we wanted passed through that point. There's only one function that fits nicely in the slope field and passes through that point, which we said on the previous screen was y equals natural log x plus 1. Okay, so the order of a differential equation is the largest derivative present in the differential equation. The previous examples were examples of first-order differential equations. Now we're going to take a look at a second-order differential equation. Here we're given f double prime of x is equal to x to the power of negative 1/2, f prime of 4 equals 2, and f of 0 equals 1. So our goal is to find the original function given the second derivative. So we probably can make the connection now that in order to find the first derivative, we could integrate the second derivative, which would be x to the power of negative 1/2 with respect to x. So if we integrate the second derivative, as we see here, we'll find the first derivative. So this will be equal to, add 1 to the exponent, that's x to the 1/2, divide by 1/2 plus c, which is going to be equal to 2x to the power of 1/2 plus c. Again, this is our first derivative since we started with the second derivative. Well, now we're given that f prime of 4 is equal to 2. So when x is 4, y is equal to negative 2. And that will allow us to determine c. So when x is 4, y is 2. So we'd have 2 equals 2 times 4 to the power of 1/2 plus c. Well, for the 1/2, that would be 2. 2 times 2 is 4. So it looks like c is equal to negative 2. So the first derivative function is equal to 2x to the power of 1/2 minus 2. Now if we integrate the first derivative, we can determine the original function. Let's go and do that on the next screen. So here's our first derivative. So to find the original function, we need to integrate 2x to the power of 1/2 minus 2 with respect to x. So here we'd have 2 times x to the 1/2 plus 1, that would be 3/2 divided by 3/2 minus 2x plus c. Let's go ahead and clean this up. We have the function is equal to, this would be 2 times 2/3, that would be 4/3 x to the 3/2 minus 2x plus c. But we were given the initial condition that f of 0 is equal to 1. So if f of 0 equals 1, we would have y equals 1 when x is 0. Now these two terms are 0, so we have c equals 1. So the original function would be 4/3 x to the 3/2 minus 2x plus 1. Okay, that's going to do it for this first video. I hope it was helpful.